As you all know, there has been significant interest in topological phases of matter in the last several decades, and in particular in topological electronic phases. Because of course they are interesting from the fundamental point of view, but also there is hope that we might be able to harvest their properties for the next generation of electronics and even quantum computation. So one of the major roadblocks has been the lack of good material platforms which realizes topological phases. So in my today's talk, I'm going to discuss how we can take advantage of strong electronic correlations arising in flat band graphene heterostructures to synthesize zero field Chern states. And also I'll discuss some interesting properties of the states that we observe. But first I want to thank to all people who contributed to this work. It was done at Andrea Young's lab at UCSB. And I want to especially mention Yushan and Manish, who are undergraduate students in the lab and who helped me to fabricate some of the devices. And also I want to mention Charles Schirhart and Marek Serlin, who also were working with me on several projects, and also who are developing nanoscale magnetic imaging. And also I want to thank you, of course, to all our collaborators from other universities, as well as to Taniguchi and Watanabe for generously provided crystals of HBM. So the experimental exploration of topological electronic phases, it started from the discovery of integer quantum Hall effect. When electrons are subjected to high magnetic field and constrained to 2 dimensions, they occupy Landau levels. And quite remarkably, this skipping cyclotron orbit along the edge of the device, it gives rise to a topologically protected chiral edge state, along which electrons can travel in one direction without backscattering. And these chiral edge states, they manifest themselves in electronic transport if we measure the longitudinal and the Hall resistance Rxx and Rxy. So when an integer number of Landau levels is occupied, the Rxy, it shows a plateau with quantized value of resistance, while longitudinal resistance Rxx, it becomes 0. And this is again just manifestation of edge state transport. So from the topological point of view, integer quantum Hall state is a Chern insulator because it's characterized by topological invariant Chern number with non-zero value. So in this case, Chern number, it encodes the value of quantized Hall conductance. And the state, it has broken time reversal symmetry. However, in this particular case, it's achieved by the application of high magnetic field. So realizing analogous topological states, Chern insulating states, but at zero magnetic field, it has been a long-standing goal. Of course, such states would be of fundamental interest, but also they might find technological applications. Furthermore, if we can substitute the role of the field with, for example, strong electronic interactions, we might be able to engineer more robust topological states, which will survive to higher temperature and will be just in general more useful. So the first proposal for zero field analog, zero field quantum Hall state, which received name of quantum anomalous Hall state, was made by Haldane. However, it took more than 20 years to actually realize one of such states, and this path wasn't straightforward. First, actually different quantum spin Hall effect was realized. In quantum spin Hall state, there are 2 counterpropagating edge modes with the opposite directions of spins. So quantum spin Hall state, it doesn't break time reversal symmetry, and it can be viewed as a combination of 2 quantum anomalous Hall states, which are related by time reversal symmetry. And this gives us an inspiration, how can one engineer quantum anomalous Hall state starting from quantum spin Hall state? If we introduce some external agent which will break time reversal symmetry, this might enable us to get rid of one of these modes, and we will end up with quantum anomalous Hall state. And this is conceptually how quantum anomalous Hall state was realized in magnetically doped topological insulators. So in this case, time reversal symmetry is broken by local magnetism of a transition element, such as chromium or manganese. Today, I'm going to talk about completely different approach towards engineering quantum anomalous Hall states. So in this approach, we demonstrate in Graphene Moiré heterostructures. In this case, time reversal symmetry is broken by intrinsic strong electronic interactions. And this has a number of consequences. One of them is actually that the corresponding magnetism arises predominantly from the orbital motion of the electrons rather than electron spin. So the basic idea is to take advantage of the incipient Berry curvature in graphene. So as you all know, graphene, it has two distinct Dirac cones, which corresponds to valley degree of freedom labeled by K and K prime here. And if we break the spatial symmetry of graphene, for example, by breaking C2 symmetry, this will open gaps at Dirac points, and there will be finite Berry curvature near those gap Dirac points. So the sign of Berry curvature will be opposite in two valleys. So the blueprint for engineering Chern insulators in graphene heterostructure is the following. We start from certain graphene heterostructure. It doesn't have to be monolayer, but in general, it will have two values, K and K prime. So the first ingredient is to somehow break spatial symmetry of the system to develop this finite Berry curvature that I just mentioned. Then the second ingredient is to introduce some additional periodic potential in the system, which will open new gaps. And this will create new mini bands. And under right circumstances, these mini bands can acquire finite Chern numbers, which again, they will be opposite in two valleys. However, still net Chern number here for such state, it will be 0, right? For both of these gaps, which are shown here. So then the final ingredient is actually to introduce strong electronic interactions. So if these bands, if they're sufficiently flat, there could be a stoner type instability, and strong electronic interactions that will polarize electrons into one of these Chern subbands. And then such state, it will have finite Chern number. So this just happens, this is just driven by the minimization of the exchange energy. And such ideas were proposed, for example, by Song and Levitov, who called such structures Chernburgers. Very interesting name. So, and yeah, please ask me any questions. I think it will be better sort of not to wait until the end. So after a short introduction, I'll talk about two such Chernburger structures which host intrinsic quantum anomalous Hall effects. This is twisted bilayer graphene aligned to HBN, which hosts Chern insulating states with Chern number 1, and twisted monolayer-bilayer graphene, which hosts Chern insulating states with Chern number 2. And then I'll also talk about some more exotic Chern insulating states which emerge at fractional lattice fillings. And in the last part of my talk, I'll discuss some curious magnetic properties of orbital Chern insulators. So after the discovery of graphene, since the discovery, the family of van der Waals heterostructures, it has grown considerably. Now it includes materials from all basic classes. And quite remarkably, by mechanically stacking atomically thin layers of these materials on top of each other, we can produce two-dimensional structures which have atomically sharp and clean interfaces. And this gives us a very versatile way to engineer new two-dimensional electronic systems. We can use different combinations of materials, vary layer thickness, and also use angular alignment between the two different layers. So today I will focus on systems which are composed of graphene and HBM. So van der Waals heterostructures, they also have another great advantage. They provide great in situ tunability. We can use electric field effect to in situ tune the carrier density in our devices, which is very convenient. Moreover, there are also some additional control knobs, such as electrical displacement field, pressure, and strain, which together with more conventional lab knobs such as temperature and magnetic field, they allow us to investigate the phase transitions in electronic system in a very efficient way. We assemble these van der Waals heterostructures using so-called dry transfer technique, which uses a polymer stamp to subsequently pick up flakes of van der Waals materials, building so-called stack. And over the years, there were a number of important improvements in fabrication techniques, which allowed to significantly increase the quality of these devices. And probably two of the most important sort of innovations, at least in the context of current talk, is HB encapsulation. When we encapsulate graphene between HBM flakes, it helps to keep it clean from adsorbates and also free from wrinkles, and also using graphite gates instead of metal gates, which helps to lower charge disorder. So here you can see an example of van der Waals stack, which is monolayer graphene encapsulated between HBM flakes, sandwiched between two graphite gates. And this is how the stack looks after we finish all our nanofabrication steps. We did some etches and also deposited contacts for transport measurement. And we can get a quantitative idea about the quality of our devices from the measurements of fractional quantum Hall effect. So we can extract so-called Landau level broadening, which for these devices, for example, about 8 Kelvin. This is slightly larger, but it's still comparable to MB growing semiconducting structures, where it's about 2 Kelvin. So now if you also take into account that this process, it could be done at ambient conditions in air, and one can train an undergraduate student how to make the stacks in 2 weeks. This just shows us that nature provides us this very fantastic way to prototype two-dimensional systems of high quality, right? And today I'm going to talk about structures which use Moiré superlattices that emerge when two graphene layers, they rotated with respect to each other. So this creates a superlattice potential. And for small twist angles about 1 degree, the corresponding period can be about 10 nanometers. And this is very convenient because it's hard to fabricate such superlattices otherwise with some top-down techniques. However, the wavelengths, it depends very sensitively on the twist angle. So fabrication of such structures, it requires very accurate angular alignment between crystallographic directions into flakes. So how is possible to do it? So if we just take two individual graphene flakes, it would be really hard to do because usually they have rough edges, and just looking at it, it's kind of hard to tell where the crystallographic directions are. So a clever trick how to actually fabricate such structures with accurate angular alignment, it was pioneered by Emmanuel Tutug's group. So the basic idea is instead of trying to use two individual flakes of graphene, we start from one larger flake of monolayer graphene, and then in the first step, we pick up only half of it by tearing it off, right? And then the first half will be already on PDMS stamp, and the second half still remains on this chip, after which the chip could be rotated by desired angle, and then we can pick up the second half, and then they will be just rotationally misaligned by that twist angle. So this is how it looks in practice. So you can see here some partial stack. This is this light region is HBM, and now it's positioned above half of this graphene flake. So on the first step, we basically pick up the first half, peel it off, then move it over the second half, add some tiny twist angle, and pick up the second half. So yeah, and we get stuck. Okay, so graphene has honeycomb lattice structure, which gives rise to celebrated band structure, right? Where there are two distinct Dirac cones in the opposing valleys of hexagonal Brillouin zone labeled by K and K prime. And this gives rise to valley degree of freedom. And because these Dirac cones are in the opposite valleys, they're related by inversion symmetry in the momentum space. This corresponds to time reversal symmetry. And of course, then there is another degeneracy, is spin degeneracy. So when we add another layer of graphene on top of the first one, which is slightly misaligned, this will have a number of consequences. So first of all, this new superlattice potential, new periodicity, it will fold large Brillouin zone of graphene into a much smaller mini Brillouin zone. And this has a number of implications. So for example, now we can use experimentally realizable electric fields to dope our system to full filling or depletion of emergent Moiré bands. And this could be seen, for example, from this measurement of resistivity. This is resistivity versus carrier density for small twist angle twisted bilayer graphene. And you can see that, for example, for devices around 1 degree, there are two insulating states at fillings of plus and minus 4 electrons per Moiré itself. And those correspond to completely empty valence band and fully filled conduction band. And these states, they happen at plus minus 4 again, because this low energy mini bands, they have fourfold degeneracy due to spin and valley degree of freedom. So, and now let's take a look actually at the structure of these emergent Moiré mini bands. They emerge because of the hybridization of two Dirac cones due to different layers by the interlayer tunneling. So the offset between Dirac cones is just proportional to the twist angle. It's something we can fully control. And the hybridization is set by the strength of the interlayer tunneling. And quite remarkably, for angles around 1.1 degree, these two things, they can produce extremely flat electronic bands. And this was first pointed out by Bistritzer and McDonald, of course. So having small bandwidths, it has important consequence, because bandwidth, it characterizes the kinetic energy of electrons. For magic angle, it becomes smaller than the Coulomb energy of electron-electron interactions, and this drives correlated physics. This was first experimentally demonstrated by the group of Pablo Herrera, who experimentally discovered correlated insulating states and superconductivity in magic angle twisted bilayer graphene. And soon after that, my collaborators and I also further investigated this system. So here you can see our measurements of resistivity in magic angle twisted bilayer graphene. So here it's shown as a function of carrier density across valence and conduction band. And again, we see this superlattice insulating states at plus and minus 4 electrons per Moiré in itself. They're slightly clipped, but I guess you have to believe me. And then for some ranges of carrier density, we also observe superconductivity, but this is not something I'm going to discuss today. So another interesting thing that there are this additional resistive states, correlated resistive states. They emerge because of the interaction-driven spontaneous breaking of spin and valley degeneracies. And so this correlated states, they emerge at all integer, potentially they can emerge at all integer fillings of Moiré superlattice. The generic feature for all these flat band graphene Moiré heterostructures. And quite remarkably, in some cases, they correspond to valley polarized states. And in such case, these states break time reversal symmetry and show quantum anomalous Hall effect. And next, I'm going to talk about one such structure, which is twisted bilayer graphene aligned to HBM.
Can I ask a question about
Yes.
the previous slide real quick?
Yeah.
So this left-hand picture, is that data? So my real question is, so G and I have been thinking about the second and third higher magic angles, but as far as we knew, most people weren't looking at twist angles that small. So can you just say something about how accessible it is to reach the other magic angles?
Well, I mean, experimentally, yes, it's in principle possible. Yeah, so this is not, I mean, this is, it's theory, right? So it's not, yeah.
Oh, okay, I see. The dark blue line looked sketchy enough that I thought maybe the small angles was experimental data. Okay.
Right. Yeah.
Okay.
Yeah, this is just theory. So, I mean, there could be like in real world system, of course, those angles, like some complicated things could be actually masking them, right? So
yeah,
but in
yeah,
principle,
I mean, I guess,
it's accessible. I mean, we can fabricate devices of different twist angles.
Yeah, I guess I thought that at the low twist angles, they maybe either disorder would dominate or you would end up with different
so.
like regions.
Because one is getting, so basically sort of the structural ground state is when they completely aligned. The closer you get into it, the harder sort of to remain in it, right? Because all the states, they are structurally some quench states, not even metastable states, right? It's complicated. So yeah.
Okay, thanks.
Right. So in twisted bilayer graphene, which is aligned to HBN, basically what this alignment does is that it breaks, for example, inversion symmetry, because HBN has two distinct atoms in its honeycomb lattice, right? That will so it breaks inversion symmetry. And this broken C2 symmetry, what it will do to monolayer graphene, it will actually open the gap, right, in Dirac column. So, and similar thing happens for twisted bilayer graphene. Also, now there is a robust gap between valence and conduction band. And this is our experimental data, which shows longitudinal and transverse resistance measured again across valence and conduction low energy bands. So again, in contrast to non-aligned twisted bilayer graphene, there is a robust insulating state now, and valence and conduction bands, they separated by a gap. So, but the most interesting feature here is that in a narrow range of carrier density, around mu equals 3, the Hall resistance, it approaches h over e squared quantized value, while the longitudinal resistance, it becomes low. And this is a sign of quantum anomalous Hall effect. So this measurement is done at some small magnetic field. And I want to note that earlier, the observation of non-quantized anomalous Hall effect in the same system was done by a group of David Goldhaber Gordon from Stanford. So I think in this case, we just had probably slightly cleaner sample, which enabled us to observe quantized response. So if we now fix the carrier density around mu equals 3 and sweep magnetic field, so we can observe magnetic hysteresis. So the longitudinal resistance, it stays pretty low, below 1 kilo ohm, while the Hall resistance, it's quantized at positive and negative magnetic field to h over e squared. And quite remarkably, this quantization, it persists all the way to zero magnetic field, and even in metastable regime when the sign of the field is reversed. So overall, this is just a manifestation of spontaneously broken time reversal symmetry with strong metastability. So in addition, we can also see some discrete jumps during magnetic reversal, which suggests the presence of mesoscopic ferromagnetic domains. So overall, this is a robust quantum anomalous Hall effect, right? So now let's talk more about the mechanism, and for this, again, let's look at low energy valence and conduction bands. So these bands are, again, fourfold degenerate due to spin and valley, and because of the alignment to HBN, there is a gap, right, which separates valence and conduction bands. Also, because of this alignment, this Moiré mini bands, they acquire Chern numbers of plus and minus 1, which are the opposite in two valleys. So at filling of mu equals 4, when all of these bands are occupied, the natural number is 0. However, at partial band filling of mu equals 3, strong electronic correlations, they drive electrons to polarize, to occupy a subset of this conduction mini bands, leaving one of them unoccupied, right? And this is driven by the minimization of exchange energy, because actually there is very high density of states, right, in this bands, and there is stoner type instability. So the corresponding state, it will have net Chern number of plus or minus 1, and it will spontaneously break time reversal symmetry, essentially displaying quantum anomalous Hall effect. So from this picture already, we can see that actually it's valid degree of freedom rather than spin, which is primarily responsible for magnetism. But there is also another argument for this, because magnetism in 2D, it requires anisotropy. However, in graphene, we expect negligible spin-orbit coupling, which will provide vanishing anisotropy for the spin subsystem. However, valid degree of freedom, it has natural ising anisotropy just because of the two-dimensional nature of material itself. So again, we sort of can conclude that this material, this family of quantum anomalous Hall states, are orbital magnets where valley rather than spin is primarily responsible for magnetism. So next, if we look at the temperature dependence of quantum anomalous Hall effect, we can learn a couple of interesting things. So here you can see the Hall resistance, which is measured at zero magnetic field as a function of temperature. And one thing we can note is that the quantized response, it persists almost up to 3 Kelvin. This is almost like the highest temperature at which quantized anomalous Hall effect has ever been observed. So it's a very good, it's an important also proof of principle that this system, like such good quantization up to high temperatures, it's an important proof of principle that this family of quantum anomalous Hall materials, it could provide clean edge states and hence could possibly be used for applications. So another thing we can learn from temperature dependence are two important energy scales. The first one is the energy scale of magnetic ordering, that is Curie temperature, which we found to be approximately 7.5 Kelvin. And another energy scale is the activation gap energy. And we found that from thermal activation of RxX and RxY by fitting them to Arrhenius law to be about 29 Kelvin. So if we now compare these two energy scales to each other, we find that the activation gap is about 4 times larger than the Curie temperature. And this is quite interesting because, for example, in magnetically doped topological insulators, the situation is exactly the opposite. And the activation gap is only is typically only 2 to 10% of the Curie temperature. And there it happens because in that system, the magnetism is local magnetism of dopants. It's essentially extrinsic magnetism. So the observation of such reversed hierarchy of energy scales in twisted bilayer graphene, again, it confirms the intrinsic nature of the effect, that magnetism in this case is the result of the interaction-induced valley polarization. So yeah, as we can see, magnetism is kind of unconventional in this system, and we found that it shows some also very interesting behavior. For example, we found that the magnetic order, it strongly couples to transport currents. So by applying either one or the other sign of transport currents, we can stabilize either one magnetic state with a positive value of Hall resistance or the other state with negative value of Hall resistance. And by switching the direction of current, we can switch the magnetic state. There is also hysteresis in this response, which allows us to do the switching in non-volatile way. So for example, by applying some pulses of current, we can switch, basically we can operate our device as a bit of non-volatile magnetic memory, right? Accomplishing read and write operations. And what's interesting about this, that in this case, the switching currents are only of the order of 1 nanoamp. So this is much smaller than in other spintronic systems. So this system has some potential for such spintronic applications. If we look at this in terms of current densities, it's also at least an order of magnitude smaller than in systems which rely on spin orbit torque. And it's actually interesting because the exact mechanism of the coupling between current and magnetic state is still not completely understood. So as I mentioned earlier, in graphene, we have weak spin orbit coupling, so that is an unlikely candidate. And at this point, there are a number of theoretical proposals which put forward different mechanisms, but sort of the jury is still out. So next, we used magnetic imaging using nanoscale microscopy to look at the magnetic structure of these domains, their switching and pinning. So this nanoscale microscope at UCSB is being developed by Charles Schurhard and Marek Serlin, two graduate students, and it takes advantage of this really tiny screed which is fabricated at the tip of a quartz tube. And in this way, one can fabricate screeds which are 100 nanometers or even smaller. So this technique, it provides both very high field sensitivity and high spatial resolution. And in this study of twisted bilayer graphene, we actually could do transport measurements simultaneously with magnetic imaging of the part of the device which shows quantum anomalous Hall effect. And that was very convenient because we could actually prepare several different states with different magnetic training, right? And then took their images at otherwise exactly the same conditions. So we pick 3 states, 2 of them, E and C, they correspond to states in which Hall resistance was quantized with positive and negative sign. And then 3rd state was some state on a partial loop which didn't show quantized response. So, and as you can see, the magnetic signal, which is in this case, it's a derivative of magnetic field sensed locally. It shows a number of features, both in the interior of the device and at the edges. It turns out that some of those features, they actually have non-magnetic origin and arise because screed also couples to temperature and electric field gradients. So actually sort of the best way to analyze and interpret this data is to take differences between 2 images, which will tell us what is the difference between state E and D, state D and C. And this is what we did. We took differences, and then we also, from this raw signal, we actually reconstructed the underlying magnetization. And here you can see the magnetization difference, essentially, between state E and D and C. So, and here you can see that, for example, this image, it shows us some finite higher magnetization in the upper part of the device. What it means is essentially that between state E and D, there is a domain in the upper, in this region of the device, which got reversed. And between state and D and C, the difference is the reversal of magnetic domain in the bottom part of the device. So now we can sort of go back and sketch out what actually was the domain configuration in these 2 cases. So in state E and C, there is one major domain which occupies entire central part of the device. And these 2 cases, the chirality of each state is different. But then in state D, there are actually 2 domains with opposite chiralities, and there is domain wall which traverses the device connecting 2 of the contacts. And then it's not surprising that actually for this state, we don't observe quantized Hall resistance, but for this 2, for E and C, we do observe quantized Hall resistance. So magnetic imaging, it allows us to directly observe these ferromagnetic domains and domain wall motion. Now, so we can conclude that basically the dynamics of these ferromagnetic domains, it's slightly dominated by pinning due to structural disorder. In this system, the major source of structural disorder is actually twist angle disorder. For example, it was imaged in study of different group from Weissman earlier, using the same technique, nanoscale imaging. So another thing we can learn from this imaging studies is actually what is the absolute, the magnitude of magnetization in this ferromagnetic domain.
Hi, could I ask a very simple question? In the previous slides, like what is the scale for the Moiré superlattice?
What is the scale for Moiré superlattice? Okay, so this is like 1 micron, right? And Moiré superlattice is about 10 nanometers. So this is like roughly 10 sites.
Oh,
no, not 10, 100, sorry, 100 sites, right? So this is probably like about 200-300 sites across.
Right? Okay, thank you.
Yeah, so I guess this is a good question. And another sort of thing to keep in mind that in these mesoscopic samples, we often deal just with tens of thousands of sites, right? Or in some cases, even just thousands of Moiré sites. So it's very interesting systems. Well, yeah, so if we look at the absolute magnitude of magnetization inside this ferromagnetic domain, so if we take line cut across this image, this part which corresponds to the domain itself, we can see that the magnetization ranges between 2 and 4 Bohr magneton per Moiré unit cell. And this is quite interesting because the maximum possible magnetization due to spin in this system would be 1 Bohr magneton per unit cell. So the fact that we observe much higher magnetization, 2 to 4 Bohr magneton per Moiré unit cell, it tells us that actually most of the magnetization, it arises from the orbital motion of the electrons. And we can conclude that magnetism quantitatively too, right? It predominantly arises due to orbital motion of the electrons. And this is quite unconventional because in most known magnetic materials, actually most of the magnetization, it comes from spin. Okay, and
can I ask a question? Are there any other materials which are known to have such large contribution from orbital magnetization?
Yeah, so there is one material, I think it's samarium aluminum, something like some doped samarium aluminum, where people notice that despite basically where magnetism due to spin and electron motion and orbital motion, they compensate each other. So they sort of cancel each other at some temperatures. Yeah, but other than that, I think this might be the first actual example when magnetization is like so strongly just arising because of the orbital motion.
Mm-hmm. And how do people detect it? So here you're telling us that you're detecting it because it's exceeding the maximum of spin, but in general, is there like a way to distinguish these?
Well, good question. Good question. Well, I think it's probably partially comparing to theoretical calculations and then maybe actually looking at anisotropy, right? How like various anisotropy of magnetism in materials probably would be my guess.
Yeah, they might respond. Okay. Yeah. Okay. Interesting. I'm not sure either. Yeah.
But in the end, yeah, I think it's comparing to calculations and some, theoretical models, which. Okay, so next I'm going to talk about different structure, right? So twisted monolayer-bilayer graphene. So this structure is composed of a monolayer graphene, which is rotated on top of a Bernal stacked bilayer graphene. And sort of why did we got interested in this structure? The motivation was the following, that at that point we knew that quantum anomalous Hall effect is observed in twisted bilayer graphene aligned to HBN and in ABC stacked trilayer graphene aligned to HBN. Both of these systems, they break inversion symmetry. We also know that in order to get a non-zero Berry curvature, one needs to either have broken inversion symmetry or broken time reversal symmetry. So the intuition is that the structures with broken inversion symmetry, they will stabilize these quantum anomalous Hall states. And twisted monobi is actually the simplest twisted graphene heterostructure, which has intrinsically broken inversion symmetry, even without any alignments to the substrate. Right, so this could be seen in the Z direction because there is one layer on one side and two layers on the other side from twist plane. But also it could be seen if we look at the distributions of local stacking in the in plane. There are these regions with local ABB stacking, which form triangular lattice, and electrons often tend to reside on these sides. But then there are these two different, qualitatively different types of interstitial sites with either ABA or ABC stacking. So you can see that there is no inversion symmetry, there is only threefold rotational symmetry in the structure. And experimentally, to fabricate such structures, we have to use small experimental trick. We actually need to find graphene flakes which have both monolayer region and bilayer region. And then we can use the same tear and stack technique, basically tear it in half and stack on top of each other, adding some small twist angle.
So the second and the third layer, they are not twisted, right?
Yes, right. So I guess it's sort of first and second. Here's AB, right? So AB is just Bernal stacked bilayer, right? And then third on top is rotated. And that's why in third layer, it varies, right? Sometimes it's B, sometimes it's A, sometimes it's C.
So will the story change if I have AA stacking for the untwisted two layers?
AA, yeah, I think it will change, but I just don't know if it's, in general, AA staking is not like very stable, right? So it's hard.
Okay.
It's always AB, pretty much. Like when we find some bilayer graphene, it always has AB stacking. I don't know. Probably AA, if possible, it's very hard to get.
Okay.
Well, but then this structure, it has another great advantage that we can tune the electronic band structure using perpendicular displacement field, D. So, and this could be seen from the following. The low energy bands here, they arise from the hybridization between parabolic band due to bilayer and Dirac cone due to monolayer, right? And it's known fact that if one applies perpendicular electric field, this will open a gap in parabolic band of the bilayer. So hence twisted monobi, it will also inherit this displacement field tunability, which is very convenient in situ node. And in our devices of this type, we have twisted monobi sandwiched between two graphite gates. So then by independently controlling these two gate voltages, we can separately tune both the total carrier density and the displacement field, which gives us full control over this system. And we studied a number of twisted monobi devices with twist angle ranging from 0.9 degree to 1.4 degree. But today I will focus on two devices with twist angles of about 1.25 degrees because they have fully developed correlated states, about which I am going to talk next. But sort of another important point I want to make here is that because we had these two devices which had essentially identical twist angle, we could sort of double check if our observations, they are generic features of the band structure. And yes, indeed, all effects that I will be describing next, they are sort of reproducible, at least qualitatively. So we can conclude that they're indeed just generic features of the band structure of twisted monobi. And I also want to mention that there are a number of other theoretical and experimental studies of this system. Okay, so next, let's look at the map of the longitudinal resistance for one of these devices with twist angle of 1.25 degrees. So, okay, this is longitudinal resistance measured again as a function of carrier density across valence and conduction band and displacement field on y-axis. And the displacement field, it enables us to tune the system over several different regimes. For example, at zero displacement field, we see only insulating states at superlattice, so-called like superlattice peaks at plus minus 4 electrons per Moiré unit site, but there is no insulating state, for example, at charge neutrality point. And this happens because, as shown by numerical simulations of the band structure, numerical calculations, in this regime, valence and conduction bands, they overlap with each other. There is finite overlap. However, at positive displacement fields, this overlap vanishes. And now we actually see insulating state at charge neutrality point. Similar thing also happens at negative displacement field. Also, in this regime, the conduction band becomes especially flat. And this is exactly the regime where we observe correlated states forming at all integer fillings of the Moiré lattice in the conduction band. I also want to point out that in this regime, the conduction band, it has Chern number of ±2. And also, I guess another note that in this system, because there is no inversion symmetry, it's not symmetric in Z direction, we in general expect completely different band structure for positive and negative displacement field. So it's not surprising that we see these correlated states only for one side of the field. So now let's focus on this region which shows correlated states, and I'll just show it here. So correlated state at nu equals 2 is a robust insulator, which suggests trivial topology. So we can measure activation gap of this state, and this activation gap, it shows some dependence on the in-plane magnetic field. So from the corresponding slope, we can extract G factor, and we find it to be about 1.6. So while it's still lower than 2, the observation of such G factor, it tells us that this state is either fully spin polarized or at least strongly spin polarized state with trivial topology. So then correlated states at nu equals 1 and 3, they turn out to be more exciting. Magnetoresistance measurements reveal that there is they show magnetic hysteresis. RxX is pretty low, while RxY doesn't quantize, but approaches to values of half of H over E squared. And such behavior, it's consistent with the states being quantum anomalous Hall states with Chern number 2. And again, this is consistent with theoretical calculations of the Chern number of the conduction band. I guess now here I also want to point out that in addition to these correlated states, and today we'll be focusing mostly on correlated states, there are also these additional features, these halo regions around each of the correlated states. There are smaller halo regions around states at nu equals 1 and 3, and they're marked by slightly different RxX, and there is larger halo region around state with nu equal 2. And this state, essentially, they mark the electronic phases with broken symmetries, while outside this halo, spin and valley symmetries, they are preserved, so the phases fourfold degenerate. Inside this larger halo, one of the symmetries is broken. It's essentially valley degree of symmetry. So the state is presumably spin polarized, this phase. And then inside the smaller halo, both spin and valley symmetry are broken. And this is confirmed by the fact that inside these regions, we also can see some small anomalous Hall effect, which tells us that time reversal symmetry is spontaneously broken, not only at this state, but also inside this entire region. Okay, so as I mentioned earlier, we don't observe perfect quantization for these states. So how can we be sure that they're indeed Chern 2 insulators? So another major evidence for that comes from the low field behavior of RxY in this system. Here it's shown in a narrow range of carrier density around nu equals 1. And in this measurement, we were sweeping carrier density for each value of magnetic field. So the fast sweep axis was x-axis, right? X direction carrier density. So if we look, for example, at highest magnetic field, RxY shows plateau as a function of carrier density, and the height of this plateau is half of H over E squared. It approaches minus half of H over E squared. And then this plateau, it persists in quite impressive way all the way to zero magnetic field. And at zero magnetic field, it suddenly changes its sign, preserving sort of the magnitude, switching to plus half of H over E squared. And this is all consistent with this being Chern 2 state. However, the most important feature here is that this plateau also shifts with magnetic field linearly. And it does it in perfect agreement with the Streda formula that describes the field evolution of incompressible Chern states. So the Streda formula pretty much it captures the fact that Chern band changes its degeneracy in magnetic field. You can think for example, about Landau level, right, which is Chern-1 band, and degeneracy of Landau level is just proportional to magnetic field. So this is fundamental property of any Chern band. So in this case, we find that this slope is in perfect agreement with Chern number 2. And there are also, if one looks closer, there are sort of like a number of fine features which have this slope. So even despite we don't observe perfect quantization at zero field, we can conclude that these states are indeed Chern-2 insulators. And it's basically here at positive field, it's Chern-2, at negative field, it's Chern-2 and the opposite value polarization. Okay, yeah, so we conclude that this is Chern-2 insulated states. So now to sum,
can I ask one simple question for the Chern-2 insulators? How experimentally, how do you tell whether this is a spin degenerate or spin up Chern equals to 1, spin down Chern equals to 1, or it's intrinsically spin polarized Chern number equals to 2 state? How do you tell that from experiment?
You're essentially asking what is sort of the exact structure of spin structure, right, of the state.
Yeah.
Well, yeah, I mean, so we cannot know, right? Like for sure, like some further measurements are needed. So what we know is that it's polarized in spin. So spin value fourfold degeneracy is completely split. But then, of course, in principle, it could be some superposition of spins, right? So I guess we cannot reject that possible scenario. Yeah.
Mm-hmm.
Yeah.
Okay.
Yeah, so sort of to sum it up, we observe Chern-1 states in twisted bilayer graphene aligned to HBN, Chern-2 states in twisted monobi. Also studies of other groups found Chern-2 quantum anomalous Hall effect in ABC stacked trilayer graphene aligned to HBN, and more recently there was also an interesting finding of quantum anomalous Hall states with Chern-1 in non-aligned twisted bilayer graphene, and there the exciting part, I guess, about that result is also that the same structure also supports superconductivity. So, and if we contrast this family of quantum anomalous Hall states with magnetically doped topological insulators, it's different in a way that for magnetically doped topological insulators, the driving factor is local magnetism of magnetic dopants or magnetism of ferromagnetic layers in the crystal. In contrast to this, in graphene Moiré heterostructures, the driving factor is intrinsic strong electronic interactions, and the corresponding magnetism is itinerant orbital magnetism. So far I've been talking about correlated states, which could essentially be explained as interaction-driven spin and valley ferromagnetism. And one might wonder, is it possible to actually get more exotic topological states which go beyond this picture of valley and spin ferromagnetism? And next, I'm going to talk about one such state which we found in twisted monobi. So when we did more careful measurements, also at lower temperatures of 20 millikelvin, we found that there are some additional correlated states which emerge at half integer fillings of Moiré lattice, at fillings of 3/2 and 7/2. And this is longitudinal resistivity measured at zero magnetic field. So even at zero magnetic field, they appear as these sharp features. And in the Hall resistance channel, they appear as some well-developed peaks at some finite field. So when we investigated how these states behave in finite magnetic field, we found that actually these states are Chern-1 insulators. And the evidence for this is the fact that the corresponding RxY at some small magnetic field, it saturates to h/e² as shown here. And then also there is this Strada formula like behavior, this peak shifts in magnetic field. And this is actually quite interesting because this new state, they emerge at half filling of spin and valley polarized band with Chern number 2, and they essentially split it in two Chern 1 subbands. So it's a non-trivial behavior. Also, at least for one of the states at nu equals 7.5, we found that it persists all the way to zero magnetic field. And this is evidenced by the observation of strong anomalous Hall effect. So it doesn't quite quantize this, but there is very strong anomalous Hall effect with Rxy higher than half of h over e squared, which is overall consistent with quantum anomalous Hall state, which is somehow deteriorated by the disorder. Okay, so the fact that these states, they happen at half filling of Moiré lattice, it tells us that we cannot describe them, explain them as a spin and valley ferromagnetism. Also, it tells us that the underlying electronic state, it spontaneously breaks spatial symmetry of the lattice by doubling the unit cell area. And this was confirmed by numerical Hartree-Fock calculations of the ground state at nu equals 7.5. So the corresponding ground state, and here you can see essentially the density in real space. The corresponding ground state is a commensurate charge density wave. So it breaks rotational C3 symmetry, but also it doubles the unit cell area. So how can we understand such state? Well, I mean, it was pointed out that if one has Chern 2, it was pointed out by Kumar in this paper, that if one has a Chern 2 band, it could be decomposed into two Chern 1 states, which live on two sublattices. And then one can treat this system essentially as a multi-component quantum Hall effect with Chern number 2, in which the role of components is played by this sublattices. So in this case, we believe that strong electronic correlations, they polarize our system into one of the sublattice polarized states. So this state is also interesting because essentially it entangles two completely different order parameters, topological and charge density wave order. So one can expect that this system might have some interesting domain walls, right, in both order parameters, and also some interesting states on defects of, for example, charge density wave order parameter. Also, this state is the first zero field realization of symmetry-broken Chern insulators. And there are two, in general, there are two types of interaction-driven Chern insulating states in a 2D lattice. This is symmetry-broken Chern insulators, which have integer Chern numbers, but spontaneously break spatial symmetry of the lattice, and fractional Chern insulators, which have fractional Chern numbers. So, of course, the dream is to find one day zero field fractional Chern insulated state. However, the fact that we already found zero field symmetry broken Chern insulating state in this system, I think it gives us optimism, reasons for optimism for this. Because if we just take an empirical approach and we look at studies of FCI and SBCI SBCI states which emerge at high magnetic fields in graphene aligned to HBN, we will find that those states they're observed at comparable magnetic fields, so they have similar energy scales. So the fact that we already see zero field SBCI in graphene heterostructures, it just tells us that actually the structures they provide very strong electronic interactions, which might be sufficient for zero field SBCI states too. Okay, so well, and let me move on to the last part of my talk. Well, I'll discuss some curious magnetic properties of these orbital Chern insulators. So quite remarkably, a comprehensive theory of orbital magnetism, it has been developed only about 20 years ago, not so long ago. And basically, according to this theory, one can calculate orbital magnetization using the following integral over all occupied states. And there are two important terms here which could be understood in the picture of electron wave packets. So the first term here, it corresponds to the orbital magnetization which can be thought as one arising due to wave packet self-rotation. So in general, this contribution, it behaves similar to just electron spin. However, the second contribution is a little bit more interesting. It corresponds to the magnetization which arises due to wave packet center of mass motion, and it especially becomes important when there is some gradient in the potential, right? So this contribution also can be thought as orbital magnetism which arises due to edge state. And this contribution has an interesting structure. It's proportional to the Berry curvature times the energy difference between the energy of the state and the chemical potential. And this peculiar dependence on chemical potential, it essentially tells us that contribution of certain state, certain occupied state to the magnetization, it can change not only with occupation of that state, but also when chemical potential is changing. So we can see that there is potential for voltage-tuned magnetization. And sort of this is at the heart of the effect that I'm going to discuss next. And actually, to understand it, we don't even need to think about it in terms of these integrals. We can understand it in much simpler terms. So the topologically protected chiral edge state carries some current, right? So it contributes to total orbital magnetization. Let us now think what will happen if we place chemical potential inside the topological gap and slightly shift it inside that gap. So what will happen is that it's not going to change the occupation of states in the bulk. However, because now there is this edge state in the bulk, we actually will be adding electrons to the edge state, and the current in the edge state will change. Consequently, the magnetization also will change. What is the change of this edge state current? So that is just given by the same equation which describes electronic transport in quantum Hall regime. So the change in current is proportional to the Chern number times the quantum of conductance times the change in electrical voltage. So you can see that actually when we sweep chemical potential inside the gap, when we change our voltage, the current and correspondingly orbital magnetization, it will grow linearly with chemical potential. And the rate of this change of orbital magnetization with chemical potential is given by this simple equation. It's just equal to the Chern number divided over non-superconducting flux quantum. So this is quite interesting, right? Because essentially our magnetization could be tuned continuously by changing chemical potential. Also, this linear growth inside the gap, it gives rise to some total jump of magnetization across this topological gap, which will be just equal to product of Chern number times the size of the gap divided over non-superconducting flux quantum. And if one make an estimate of what that jump of magnetization will be for this topological graphene Moiré systems, one will again get some number which is larger than maximum spin magnetization. So even from this sort of back of envelope calculation, one can find that the total magnetism predominantly arises from the orbital motion of the electrons. Okay, so this is quite interesting, this sort of linear change of magnetization inside the gap. However, there is something, I guess, even less counterintuitive, that it turns out that the magnetization doesn't only change linearly, it often crosses zero actually inside the gap. And this happens because of the interplay between two contributions to orbital magnetization, the edge state contribution and the contribution to orbital magnetization due to electrons in the bulk. And while in general this bulk contribution, it will depend on the details of the band structure, on the bandwidth, on how Berry curvature is distributed in the band, there is a general trend that this bulk and edge state contributions, they have the opposite signs. And this is, for example, even the case for integer quantum Hall effect, which could be seen sort of from this simple cartoon explanation, right? Because the cyclotron orbits in the bulk, they have direction chirality is the opposite to that of the edge state, right? So when first we fill in the bulk band, our magnetization, it will grow in one direction, but then when we start filling inside the topological gap, the edge state, it will sort of bounce back and cross zero. So, okay, so now let me actually show you the evidence that this is indeed what happens in our experimental systems. So we found this in the mu equals 3 state in twisted monobi, which is shown to insulators. So when we studied how magnetic hysteresis changes as a function of small doping around this state, we found something quite unexpected, that at some value of doping, the direction of the hysteresis loop, it suddenly reverses, right? You can see, for example, that this loop has the opposite sort of direction as this one. And this could be also sort of viewed from the other point of view, that if we look what magnetic state is stabilized by positive magnetic field, so at some negative dopings, we stabilize in magnetic state which has positive Hall resistance. But then it suddenly switches to the other magnetic state with negative Hall resistance. And as this transition happens, the magnitude of RxY actually it remains nearly unchanged and is still close to the quantized value. So this suggests that actually the sign of the coupling between magnetic field and magnetic state, which is magnetization, it changes sign at this point. So I guess let me explain also in slightly different way, right? So if we imagine that our magnetization, it changes linearly and crosses zero inside the gap for one magnetic state with value polarization K prime, then in the other magnetic state, because they're related by time reversal symmetry, the magnetization, it will be exactly the same, but with the sign minus, right? So here already from this, you could see that the magnetic state, which is stabilized by positive magnetic field, it will switch at this inversion point from K to K prime. And this is exactly what we observe in experiment. So this is the measurement of RxY near nu equals 3 at some higher temperatures where there is no metastability and hysteresis. So in this case, we were probing directly the value polarization of the ground state. But still RxY, it remains close to the quantized value, so we can use the sign of RxY to label, to identify the value polarization. And you can see that actually the value polarization changes in this checkerboard pattern. It changes both when we change the sign of the field, but then also it switches across nu equals 3 when we dope the carrier density. So what enables this effect in orbital churn insulators? There are two important factors. First of all, it's important to have spontaneously broken time reversal symmetry at the level of electronic subsystem itself, right? So if we have some other extrinsic factor which breaks time reversal symmetry, for example, like in magnetically doped topological insulators, where it's some magnetic dopant which breaks time reversal symmetry, this will prevent this effect from happening, right? Because both states, they need to be exactly on the same footing. And then another important factor is that spin magnetization must be weak and decoupled from the orbital one, right? So all this dynamic, it could be prevented if there is strong spin magnetization, which is locked with the orbital magnetization. So this makes this effect unique to this family of quantum anomalous Hall effects, orbital churn insulators. So this effect, it enables us to use electrical voltage to switch the magnetic state. However, we found something even more exciting, namely that these states, they actually can be strongly metastable. This metastability arises likely from the fact that there is no states with intermediate value polarization. So we found that there is a hysteresis.
Hi, I have a quick question about the previous slides. So usually when the sign of our XY change, there is also a possibility that maybe it's due to the carrier type change, like it changed from hole carrier to electron carriers. So how can we differentiate that thing with this like orbital magnetism?
Yeah, so good question. So yes, so we can do it because so at zero magnetic field, no, like first of all, because this whole resistance is quite high, it's close to h over e squared, right? And even at low magnetic fields, right, it approaches this very high value. So actually, if you would expect some classical quantum Hall signal, it will be much weaker and it will be field dependent, right? Here we have essentially field independent RXY, right, which is close to the quantized limit. So it's classical somewhere here. You can see a glimpse of regime where it's classical, and you cannot even see it essentially on the scale, right? Because it's much weaker.
I see.
Right. This is all essentially it's within a quantum Hall plateau, right? It's all like within quantum Hall plateau. So because of disorder in the system, actually this plateau has some finite width. It's sort of easier to, I guess, like was easier to see on some images that I was showed earlier, where you could see sort of this plateau which persists down to zero field, right? And this is the same plateau here. It's like slightly washed up by higher temperature, but yeah, it's the same. Okay.
Yeah, kind of. Yeah. Thank you.
Yeah, so we actually found that there is magnetic hysteresis not only with respect to magnetic field sweeps, but also if we sweep carrier densities, it is gate voltage, right? So you can see these two sort of interpenetrating hysteresis loop in perpendicular directions as a function of field sweep and carrier density. And such sort of double metastable behavior, it allows us to actually accomplish switching of the magnetic state by either small excursions of either magnetic field or carrier density. And this switching, it happens with perfect fidelity, and also it's non-volatile, right? So essentially, we did this type of measurement where we were switching it with either carrier density of magnetic field to show that the both operations are completely equivalent, right? Doesn't matter how you switch it, the outcome is the same. Of course, from practical point of view, switching using gate voltage, it's much more useful, right? From the point of view, some applications. And in fact, electrical control of magnetism, it has been a long-standing goal. There has been some progress in this direction in multiferroic systems. However, this effect in orbital Chern insulators, it provides us a conceptually new way to electrically control magnetism. Moreover, in orbital Chern insulators, we actually controlling not only the magnetism, but the topology, that is the direction, the chirality of edge states. So we electrically switching the chirality of edge states. So the applications of this effect, they can take advantage of electrically patterned magnetic domains and chiral edge states. Such applications can include low power magnetic memory and logic devices. Then in other possible applications are actually reconfigurable in compact circulators for microwaves based on chiral edge states. And finally, such reconfigurable electrically controllable quantum anomalous Hall states could be useful for devices where it's combined with superconductivity for novel electronics and also manipulation Majorana zero modes. Okay, so yeah, today I told you about intrinsic quantum anomalous Hall states, which can be engineered in graphene Moiré heterostructures, and I considered sort of describe you two systems: twisted bilayer graphene, where we get Chern 1 states, twisted monolayer bilayer graphene, where we get Chern 2 states. And The magnetism in this family of quantum anomalous Hall states, it arises from the interaction-driven spontaneous value polarization, and the topological nature of magnetism in these materials, it gives rise to this interesting effect, which allows us non-volatile electrical switching of topological and magnetic order. And moreover, we can also see this higher order correlated states, which occur at half fillings of Moiré superlattice, and which are zero field symmetry-broken joint insulators. Yeah, and with this, I would like to thank you, and I would be happy to answer any questions and continue the discussion.
So can I ask you a question?
Yeah, sure.
I have a question, two questions, mostly experimentally oriented. Is there any reason people don't do proximity superconductivity in twisted bilayer system experimentally?
No, I don't think that there is any strong reason. It just didn't.
The reason I'm asking is motivated mostly because of this. I don't know if you're familiar with chiral Moiré fermions system. The 2D, they try to, there's controversy over they really actually observe chiral Moiré in the quantum anomalous Hall superconducting system. And if this system also is really a quantum anomalous Hall, people can try to see that maybe here Moiré can be easily at least be seen a little bit more easier because of this huge activation gap. And but that's my confusion. But nobody looked at it. Whatever paper experimentally I'm looking at, it's just basically this magnetic doped TIs plus superconductivity. I thought that there is a strong reason.
No, there is no strong reason. It's a good idea, and I think it's on to-do list. On to-do list, there are just like many other things, right? It hasn't come to that yet. Yes.
The other question is, have you guys started to look at the stack of this twisted system? Taking this quantum anomalous Hall system and keep stacking it to probably either getting a 3D quantum anomalous Hall insulator or maybe some exotic semi-metallic system.
Yeah, I mean it's an interesting idea. I guess like now sort of the main experimental difficulty is still fabricating this type of structures, and then the complexity, of course, it will grow exponentially with the number of twisted planes, right? So now I guess state of art people do like 2 twists, right? It's either alignment to HBN or it's, for example, this twisted trilayer with central plane twisted, right? So yeah, I think it's just that is the limitation. Of course, in principle, yes, one can think about some more extended structures where you have some interesting alteration of twist angles which persist sort of over many layers. But yeah, it's just practical difficulties for doing that.
Yeah, thank you.
I also have a question. I should have asked this at the very beginning. So in your, I hate to say earlier work because it's only a year old or so, when you saw the quantized anomalous Hall, what's the asymmetry between it's observed at, I think, it's observed at filling 3, but not at -3, right?
Yes, right.
So do you guys understand that?
Well, so in general, in twisted bilayer, actually there is no, valence and conduction bands, they're quite asymmetric, right? Yeah, so they're not symmetric. In general, so none of the states are actually, there is like no symmetry sort of whatsoever. So definitely that asymmetry, it's somehow much stronger than just in monolayer, right, or bilayer graphene.
Yeah, it doesn't look to be that big, but okay, you're correct. There's nothing that prevents it. There's no symmetry that prevents the fillings from being different, and in fact, the band structures do not have particle hole symmetry. So
yes, right.
There's nothing that prevents that.
It's like relatively strongly asymmetric. Even calculations show, just simple calculations shows that there is strong asymmetry, like density of states is asymmetric and so on.
Okay. The other question would be comparing nu equals 1 and nu equals 3. But there, I mean, since everything is due to correlations and correlations depend very strongly on density, there's, there's no reason to expect those things to be the same.
I think so, right? So definitely there are some similarities between those two states and the fact that they are both Chern 2 states. But for example, we can even see from sort of Curie temperature, right, that state at nu equals 3, it just appears to be more robust, so it obviously has slightly larger gap. Why exactly that happens? Again, probably some symmetries in the structure, even gap. So for example, gap at Church neutrality is not the same as at nu equals 4, right? So even that alone will contribute, but also as you feel it, of course, you have sort of different, probably you have different screening, right, from already filled bands. So that also could contribute.
Hi, Gregory. Thanks for the very interesting talk. I have one questions. So as far as I know, there are some theoretical proposals about the fractional quantum Hall states in the C number equals to 1 or 2 bands. Have you ever tried to see that? And from the experimental point of view, which tuning knob, for instance, the screen length of the interaction or the flatness of the band, you think could help to find this lattice version of fractional quantum states?
Yeah, it's a good question. I mean, I guess what we could do is sort of just to look for them, right? I mean, so far we haven't found anything. Sort of the closest thing we found is this zero field symmetry-broken Chern insulated states. Well, of course, one would probably look for this type of states in structures which have, so the higher the density of states, in some sense, like the better, right? So you want to find structures with even flatter bands, and how exactly that could be achieved, it's also sort of a good question. So maybe one can, I mean, so it probably either will be like some slightly different type of structure, which is not yet, hasn't been explored yet, or maybe it's already some existing structure, like even, for example, twisted monobi, but for example, maybe under hydrostatic pressure, right, or something like that, because that will change the strength of interlayer tunneling and also will modify the band structure. So I think it's essentially, it will be like some interplay between bandwidths and Coulomb energy, in the sense that maybe it's better to have structures with slightly larger, with slightly smaller Moiré wavelengths, right, where the sites are closer to each other, because that will enhance interactions between electrons. But also, if one can do that and still have the same bandwidths, right, then it might help. But if it also will increase bandwidth, that it might not help. Right? So.
Yeah, thanks.
I was also wondering about the current switching quantum anomalous Hall direction. Is there a, you have in some stuff that you talked about, you have some nice, simple pictures to understand stuff. Is there a way to understand that? You said the mechanism is under debate, but I was wondering what's the simplest possible mechanism?
Well, so yeah, that's actually not like that obvious in a sense, because if you like think about it, I mean, so something must break symmetry, right? Like why certain direction of the current favors like certain value. So I guess there are two sort of two options. First of all, it could be just because of certain asymmetry of the device itself. For example, one edge state on one side of the device is like longer, right? And the other one is shorter, and that could create like this difference between current in one direction and the other direction. Or it could be just the importance of current sort of, if you have like some small current in the bulk, it will directly dope one of the valleys, right, versus the other valley, right? It's sort of direction of the current essentially with respect to crystallographic directions, right? That somehow you dope in one of the valleys stronger than the other. It's probably either like, yeah, those two mechanisms which are the primary suspects, but could be something else too, right?
Mm-hmm.
So definitely there is no such clean picture as we have, for example, in the case of this electrical switching, where we understand it very well. Why it happened.
And I guess if you have HBN, that already does break the symmetry between valleys, crystal symmetry, but I don't think that's enough. I don't think that's enough to break the kind of directional symmetry.
Right, it seems so, right. Yeah, I agree.
Okay.